Okay, hello everyone. Let's resume where we left off. So, light and electromagnetic radiation. So, what's electromagnetic radiation? Well, so it's electromagnetic radiation is pretty much the a form of energy matter gives off in the form of waves, or pretty much energy that is radiated or transferred through space in the form of um, oscillating magnetic and electric fields, and that has to do with more simplistically speaking. That's a fancy way of saying they move like in waves. Okay, so electromagnetic radiation or light, they tend to move in waves, and they have a component that is magnetic. So the wavy the it can interact with a magnetic field and also can produce an electric field based on the properties of energy. So really what's happening is that electrons are moving and they're generating charged particles. They give off electric fields, and also they can interact with a magnetic field and generate and pretty much generate a magnetic field as well, spinning around its axis. Okay, so moving charges, they usually have this. If you remember from physics, but I'll explain also that pretty much any charge moving in a circular loop or a circular orbit, they can, well, not circular, but they rotate around an axis. They do produce an electric field. Okay, so pretty much any source of light or source of energy in the world, they can exist as in space, and they emit electromagnetic radiation. So that's why when we deal with light, we have to kind of be careful about the light source, because depending on what kind of light source you use, it can have low or high energy. Okay, so this chart, I would say you want to memorize this chart. That radio waves, they tend to have the longest wavelengths, and then as you go up to more higher forms of energy, so usually we say energy of radiation is proportional to the frequency. So the higher the frequency, the more energetic the source of light will be. Okay, so we see here right in the middle, there's visible light right here. Okay, so that's the area of the spectrum that we can perceive. We can see colored light, right? We can't see infrared. We can't see waves from the TV, radio waves, X-rays, gamma rays. They all look invisible to us, but they exist, and they are high forms of energy. X-rays are used to get images, high contrast images. Ultraviolet radiation is from the sun. We wear sunblock to protect ourselves from ultraviolet radiation. Our bodies cannot handle ultraviolet radiation, and that's because ultraviolet radiation has the potential to break chemical bonds. So that's why it's important that we do not expose ourselves. Okay, gamma rays and cosmic rays are pretty much energy waves that come from these in space. Gamma rays are emitted from the nucleus of certain nuclear reactions, so they are of high energy. So think about if you want to do chemistry on an atom's nucleus, you need to rupture it, and that takes a vast quantity of energy. So energy that we cannot get normally under a chemical reaction. So chemical reactions, we don't destroy atoms. We're simply changing the connections or the electrons between them. So we're not actually interacting with the nuclei, which contains the atom's pretty much the atom's identity and stability in the form of protons and neutrons. So that's most of the mass. So we're actually not messing too much with the mass of the atoms. We're kind of thinking how to combine atoms through their electrons. So that's why chemical reactions are usually not able to completely change an atom's identity because it can't mess with the elements. Okay. And then here is a little spectrum of the colors here. Red is usually 700 to 650. 600 is orange. Yellow is around 550. And then, 500 to 550. Or I would say 550. And usually green is in between on the order of 500, and then blue is usually from 500 to 450 or 400, and then anything below that gets into the region of ultraviolet or violet, and then eventually you'll go into ultraviolet light. Okay, so ultraviolet light is usually on orders of like one very small wavelengths of light. Okay. All right. So see on this graph here, as the wavelength increases, our frequency decreases here. Okay. So frequency and wavelength are inversely proportional. As the frequency increases, your wavelength should decrease because you can't really have a high frequency if your wavelength is long and large. So that's why frequency is inversely related to wavelength. So that's something we just have to remember. Okay? All right. So when we're talking about light, if light can be represented as waves, then we say all these different forms of radiation, they travel at the same speed. And that speed is called c. C, which is the speed of light. Well, I won't put in parentheses. That's probably not a good idea. C, speed of light. So we have determined the speed of light. The speed of light is approximately 2.998 times 10 to the 8th meters per second. Okay? So that is the speed of light. All right. However, what's different about these different light forms or radiation, sources of radiation, they differ in their wavelength. Okay, and frequency. So we see here for every combination on the spectrum, there is a different frequency and wavelength of these sources of electromagnetic radiation. So light and things related to light, they carry energy and they're related by a wavelength and a frequency right here. Okay. So what we can say here is that the product of the frequency times the wavelength of electromagnetic radiation is always going to be equal to the speed of light. So that's something we should probably highlight here. So we can say frequency times wavelength equals the speed of light. Okay? So that's something we can always remember. And I'll provide this equation on quizzes and exams for students, okay? All right. So as a result of this, electromagnetic radiation, or EM, that has a longer wavelength has a lower frequency or smaller frequency. Okay? And radiation with a high frequency has a shorter wavelength. Okay, so it works vice versa. All right. So now let's do an example here. Calculate the frequency of red light that has a wavelength of 700 nanometers. If the speed of light is 2.998 times 10 to the 8th meters per second. So don't worry too much about like the exact numbers for these types of EM radiation. What you should think about is like where they fall on the spectrum, like which one's shorter, which one's longer, and so forth. But don't worry too much about the exact frequency numbers or wavelength numbers. Okay? All right. So this this problem, we're going to use the equation delta lambda times frequency equals the speed of light. Okay. So we're solving for frequencies. So we're going to set up our equation. Frequency equals C over lambda. And then when we plug everything in, we get 2.998 times 10 to the 8th meters per second. Okay. And then we divide this by, okay. So we have 700 nanometers here, right? However, we need to get the units the same. So we know that so we have 1 meter equals 10 raised to the 9th power nanometers. So that's the conversion we need to know. So nano means 10 to the 9th nanometers for 1 meter. Okay. So in this case, we can say 1 meter here is equal to 10 to the 9th nanometers. Okay. And then if we solve for this equation here, meters will cancel out, and then nanometers will cancel out, and we're left with inverse seconds. So in this case, we get 4. Oh, sorry, I forgot my sig figs, didn't I? Let's put our sig figs. So let's look at our answer here. So remember, conversion factors don't count in sig figs. So we're looking at our speed of light and our wavelength. They both have 4 sig figs, and we're dividing in this case. So we're going to have 4 sig figs in our answer. So 4.283 times 10 to the 14th inverse seconds. So that's a really high frequency. So this kind of makes sense, right? Because light waves, they're moving on the order of pretty much almost 1 billion meters per second. So, well, not 1 billion, but 100 million, like 100 on the order of 100 million meters per second. So it's going to be a really high frequency. So don't worry if your number's too big or too small. In this case, frequency should be really big. And then for the case of wavelength, it should be a really small number. All right. So here we're thinking on particle sizes of really small. So things you can't see. So even smaller than microorganisms, we can't even see them. Okay. So this value makes this value will be correct. All right. Okay, so let's move on to the next topic here. All right, so here we're kind of getting more to quantum mechanics now. Atomic spectra. So if we think about the continuous spectrum, So, eventually, if you heat objects. Oh, sorry. There's a typo here. My apologies. So, objects at high temperatures, okay, they emit a what we call a rainbow of colors. So, you just think about rainbow, right? A rainbow has pretty much all the colors, all like of the primary and additive colors you see. So, all the spectrums of the color that we just saw, right? It's a really interesting thing there, and that's because usually, when it rains, light gets diffracted through the water, and it actually can separate into the colors. So that's pretty cool. So that's how the rainbow you see. Okay, so if we were to heat up an object at a really high temperature, and you were to kind of use some diffraction grating and perceive all the light, you would actually see a continuous band of color. And I think this will be an experiment we do in a few weeks. So we'll actually be able to see this. We'll be able to confirm this in lab. It's really cool. So the kind of spectrum it looks like the visible spectrum of EM radiation. So say you take some fancy like telescope, in this case a spectroscope, and you looked at like say the sun, you would actually see a spectrum of light in the spectroscope that looks like this. It looks like this color of light, and so it looked like these continuous spectrum. We call this a continuous spectrum because you see in the spectrum here, there's no like spacings between the colors. The colors are all seamlessly connected together, right? There's no spaces of the absence of light or darkness between the colors. So this is what we call a continuous spectrum. So for objects at very high temperatures, this is what we see. So if you have really old light bulbs, like incandescent light bulbs, so the light bulbs that are pretty much, they're translucent, and then they have a wire fitting in the middle, and you can really tell because these are really old light bulbs you see in your garage, you see in old housing. They are what also emit continuous spectrum like this. Okay, so that's a continuous spectrum. What we're concerned now with quantum mechanics is when elements emit light. So when we pass energy through the gas of an element or a gas discharge tube containing an element, when those will also emit light because we're exciting the electrons in the atoms, and they tend to emit light. And when we view that light through a diffraction grating or a slit, it can actually separate the individual colors of the light. So like in this picture here, we see here, instead of a continuous spectrum, you're going to see areas of darkness. So this is pretty much, so you see these dark shaded gray areas here. Those are areas of no light. And then on the individually, you see these bands of colors. So violet, blue, green, and red. So for example, this would be the line spectrum for hydrogen. So each element can be identified by their line spectra. Or what we call this line spectra because it's not continuous and there's only specific regions of light being observed. So many other elements can be identified with their light spectrum. So it's kind of like a fingerprint, right? You have a specific fingerprint for each individual. Each element in this case will have a specific light spectrum. So that's how we can identify elements in that way, using a light spectrum. Okay? So it's not continuous. So this kind of puzzled physicists and chemists at the time, mainly pretty much physicists, because they couldn't explain this observation with classical physics or classical mechanics. So then Niels Bohr came around, and this is how he developed this observation. Is one of the cornerstones of his atomic model of the atom, and where we say, okay, atoms, The electrons, they are composed of certain particles that are giving off this light, and we say since it's not continuous, these electrons, they must be housed or homed in the atom in different energy levels. So we'll go over that in the next video, okay? So, but to summarize here, the line given off by this hydrogen gas, when it's excited, it'll emit light. And instead of a continuous spectrum of colors, we see only individual bands of light. So that means only certain wavelengths of light are being emitted. So that has some pretty important implications for how we understand electrons and how we understand the structure of the atom. Okay, so the next video we'll start going over what these lines mean. Okay, so I'll see everyone in the next video.